All right, welcome to the first lecture for week 8. Today we're going to be looking at fluids, which will lead us on to a discussion of buoyancy. As usual, I'll jump over to the lecture slides and we'll get started on there, but I'll remain up in the corner and we'll also jump back and forth with the document camera and so on. This will be 2 separate videos for the lecture content and another one for the questions, as I've been doing. So today the first one will be slightly shorter, I believe, but we'll see how we go. Our lecture is on fluids. Forgive the subtitle, it's week 8, not week 7. That'll be corrected for the online version of the slides. So our goals today are to define density, pressure and relative density, calculate pressure from depth of fluid, calculate the force on the inside of a vessel containing a liquid, and distinguish between pressure, gauge pressure and atmospheric pressure. This first video, we're just going to do the first couple of those, or actually just that first point, those definitions. We're going to think about what we mean by these different terms, and then in the second part of the lecture, we'll actually start applying and calculating some of these things. So firstly, just a recap, states of matter. All matter is made of atoms, so we just want to remember that. It's going to be very useful for our analysis of the different properties that we're going to look at, including pressure and fluids and things. To recall what each state means. So solid, all the atoms are fixed in their place, they can't move. Liquid, they can move around, but the volume of the liquid is pretty much fixed. It can't get bigger or smaller. You've got a certain volume of liquid and it'll just sit in whatever you put it in. Whereas a gas will expand to take up the volume you provide it, and the particles are all flying around. So keeping in mind that picture of what we mean by the different states will help us conceptually with our understanding of pressure and some of the concepts we'll meet. Firstly, fluid, a definition. We've met liquid and gas. Fluid can be either a liquid or a gas. The definition is that a fluid is a substance that conforms to the shape of its container. So that is that fluids can flow. Cats are often depicted as fluids. Properties of fluids. When we deal with solids, we talk about height, width, and length, these sort of things we can measure because they stay the same, because all the atoms are fixed in place. But they're not fixed in place with a liquid, so it makes no sense to talk about the height of actually, we will talk about the height of a liquid, but we'll talk about depth, we'll just often call it height. But the length and width and things doesn't really make much sense. So we can refer to the containers that hold a liquid, or a fluid, but we can't really refer to the dimensions of the fluid itself. But what we can do is refer to its mass, its pressure, density, volume, temperature, and even viscosity, although we won't deal with that today. But there are these different properties we can bring into it. We just can't necessarily stick with the same ones we had when we dealt with solids. Density is a term many of you will have met, but just to recap hopefully everyone's met this before, but just a recap is that density is how much mass is stored within a given volume. So it's density, which is the Greek letter rho. It's a curvy symbol that looks kind of like a P, but it's not a P. That is equal to the mass over the volume. So it doesn't actually matter what the mass or the volume of the substance is. What matters is that ratio. How much mass do you have per unit of volume? From that, we should be able to determine the units quite easily. Mass per unit volume, so mass over volume. So there are plenty of options. Kilograms per cubic meter are obviously the SI units. We're all familiar with SI, kg being for mass and meters for length. So kilograms per cubic meter. But equally valid are grams per cubic centimeter, kilograms per liter, grams per mil, or any other combination of mass divided by volume is acceptable. As usual, when we're converting and discussing with other people, we'll try and stick with SI units, but sometimes we do end up calculating in non-SI units just out of ease of use for certain measurements that we've taken. And if you've studied dimensions, hopefully you've all covered that at some point, but with dimensions, mass per, m, L to the minus 3, so a mass and then length cubed on the bottom is the dimension. There's some examples here. There's a range of them. You can see hydrogen gas being the lowest, a whole cubic meter. Now this can be a little bit deceiving to think about a cubic meter. People don't often visualize the space. So what can be a good exercise, and feel free to stop the video and do this now, is to actually map out a cubic meter. If you have a ruler, great, you can actually measure it. If not, you can just pace it out. Usually one normal to large step of a human is a meter, but just try and figure out around about what a meter is. 3 lengths of A4 paper is just over 90 or just under 90 centimeters, which is almost a meter. So there's different ways you can visualize it, but try and map out a cubic meter. And then imagine a block that size of these different substances. So a block that size of air would weigh 1.29 kilograms, a whole cubic meter, and it's only just over a kilogram. Helium gas and hydrogen gas are less than air. That's because helium and hydrogen particles, the actual atoms, are a lot smaller than the ones that do make up air for the most part. We're mostly nitrogen with a fair chunk of oxygen, and those are a lot heavier than helium and hydrogen are per atom or per molecule in the case of ones that go into molecules. And so that means that overall for that cubic meter we have more mass because we've got heavier molecules or atoms. But then going up, you can see oxygen is heavier than air on average. Right, again, same reasoning. And then those are all small though. Those are all, 1.5 oxygen gas is still tiny. We then jump up to woods. So various wood has different densities, but we can see pine is 373, oak 710. So just keep visualizing that cubic meter, that big block of something, a big block, cubic meter of wood. Could be anywhere from 300 to 800 cubic kilograms for that 1 cubic meter. And then we get into some liquids. We've got alcohol, benzene, and fresh water. And then on the top of the next table, seawater. Glycerin's another kind of liquid. So we've got these different liquids. They're sort of averaging around about water, which is 1,000 kilograms per cubic meter. So that big block of 1 cubic meter that you're imagining of water weighs 1,000 kilograms. All right? So water is pretty heavy compared to obviously air and water and wood. And then we get into some metals. We've got aluminium is 2,700 is the lightest of the metals. That's why it's a very useful material to build things out of, because to make the same size object out of aluminium will obviously have a lot less mass than that object made out of something else like iron or steel. And going up, you can get up to platinum, which is 20,000 kilograms for that 1 meter cubic block. So it can be difficult to visualize. A lot of the time when I'm talking about problems, I always ask you to visualize or think about the scenario and try and get an estimate of what you expect the answer to be. And I realize that with density that can be difficult, but hopefully if you can sort of keep in mind some of these ideas. Air is a bit over a kilogram for a cubic meter. By the time we get up to water, we're looking at 1,000. That one we expect you to just remember, right? Water is 1,000 kilograms per cubic meter. You should all know that by heart. And then metals starting at around about 3,000 for aluminium, going up is, well, up to 20,000, but very heavy for some, very dense for some metals. So if you can roughly keep in mind that scale, it can help you determine what you would expect for certain experiments or certain problems, certain scenarios. And that is a very valuable insight to have when you're dealing with these kinds of problems. So density is great. We can compare different subjects' densities, but relative density can be very useful as well. If you've got one certain substance and you're going to be comparing it with a lot of different things, it can be useful to have relative density. So comparing all of those as a fraction of that reference material. So what we're looking at, we call it rho relative density, is equal to the density of the object you're looking at, or the substance you're looking at, over your reference density, rho naught. So that's just a definition, relative density. It's a ratio of your one that you're considering over some reference material. Because densities have the same units on top and bottom, then they will cancel out, but it does mean that they have to be in the same units. Right? You can't go and take a grams per mil for the top density and then use kilograms per cubic meter for the bottom density. You have to convert them both to the same units. Doesn't have to be SI, just has to be the same units. And as I said, they'll cancel out, so we'll be left with no units, and leaving relative density as a dimensionless quantity. You may or may not have heard of dimensionless quantities before. They are something that physicists tend to like. We tend to look for them because dimensionless quantities mean that you can always compare them. Right? You can compare the dimensionless quantity for different things without having to worry about whether they're in the same units, because there aren't any units. So it can be very useful. This image is a common one that you'll see floating around the internet, or very similar variations of this, and I just shamefully stole it from the internet to put in here, and it just shows these different densities of different things. So honey is the most dense of the liquids, so the liquid names are on the left. Honey is more dense than corn syrup, which is more dense than maple syrup, so the denser one sits underneath the less dense one, and then so on up the liquids, with lamp oil at the top being the least dense. Sorry about that, sensitive mouse again. On the right hand side, you've got the names of some solids that they've put in there. So you can see the Bolt has gone straight to the bottom because that's a metal, and we saw that metals are generally denser than all the liquids that we saw. Popcorn kernel, though, will sit between maple syrup and corn syrup. A dice is hidden in there in the milk, so it's about the same as milk but less dense than maple syrup. And then we've got cherry tomato, which is slightly more dense than water, but about the same as dish soap. And that makes sense when you think that a tomato has a lot of liquid in it. That liquid is water, but it's got some other stuff which will increase that density slightly. Beads, they haven't told us what kind. Soda cap and a ping pong ball is obviously mostly air, so that's going to be overall quite low density. So that's just a useful sort of image to think about what the relative densities actually mean. So we don't know the actual densities of any of these objects, apart from water, assuming it's pure water, but it does tell us that we can just think about how these things will interact based on their relative densities, which one is more or less dense than the other. When we want to compare different things, it's useful if we do it all with one specific reference material. And since water is very common and very easy to work with, that makes a great choice for a reference density. So what we've done is define a specific gravity as being the relative density of some object to water. Right? So water is the reference density. Since pure water has the same density as pure water, unsurprisingly, the specific gravity of pure water is defined as 1. Right? It's just the density of water over the density of water. So then we can compare everything else with the density of water and get these terms a specific gravity for all the different substances. And as we'll see, the specific gravity being more or less than 1, i.e. more or less than water in terms of density, can tell us about the system. So that's, we'll continue on with the pressure actually. So if you have a cardboard box and you have a heavy object and you go and stick it on the cardboard box, right, the box will support the object. As long as it's not too heavy, the box will manage to support it. Suppose the box is empty, say you've got a big jug of water or something, you put it on the box and the box manages to support it. But now instead, imagine that you've fixed, say, 3 nails to the bottom of that jug of water. Right? I'm actually just going to jump back to the camera for a moment. So imagine you've got that jug of water on a box, right, and you put it on the box and it stays there, but now you go and put 3 nails on the bottom of that jug of water. So you've got these nails pointing down, and you then balance that onto the box. Right? That jug that's full of water is going to push those nails right through the cardboard box. Hopefully we all can imagine that. Right? But the actual weight force hasn't changed. I mean, it's increased by 3 nails, but essentially there's not a great difference in the weight force of that jug full of water, because the nails would be relatively small comparatively. So if the weight force hasn't really changed, the box definitely hasn't changed. We're still using the same box, yet we get a different outcome. In the first case, we didn't deform the box, it just supported the jug of water. In the second case, we did deform the box. The nails pierced it. They actually broke the cardboard. So the question is, why are these different? Even though we've got the same forces involved, why do we have a different outcome? And as many of you are probably aware, the difference is the area over which the force is applied. So as a little demonstration on the right, illustration, I've drawn a brick on a shelf. The brick on the top shelf is lying on its side, right? And the brick on the bottom shelf is standing upright. And so the brick on the top has a greater surface area contact with the shelf, brick on the bottom has less. And so we know that there's something different. Same forces involved. We have the exact same weight force, the exact same normal force, but the area over which that force is applied is different. And we intuitively know that that means we've got a different outcome. And so we need some way to define that. And so as you all probably have met before, hopefully, we have pressure. Pressure is the way we define that ratio of force and area. So the same force over a smaller area means higher pressure. In the case of the jug of water balanced on nails on a cardboard box, the area gets really, really small, the tip of those nails. And so now we've got this really high pressure at those 3 points where those nails are. And so they'll just pierce the box. The box can't withstand that kind of pressure. But when the jug was as a whole was sitting on the box, the area was the whole bottom of the jug, which was big enough that the box didn't deform or break. So that pressure can define what's going to happen, or can determine what's going to happen. So we need to be able to understand and calculate things using pressure. SI units for pressure are newtons per square meter, as we'd expect, newtons over an area, a force over an area. We also call them Pascal because pressure is so common. We gave it its own name, Pascals, which is named after Blaise Pascal, who we'll see in a moment. And we write the symbol capital PA. So technically, Pascal as a unit has a lowercase p, but if you write the abbreviation PA, we put an uppercase P on it. Obviously, the name Pascal has an uppercase, but this is just the convention. People aren't normally going to be too picky, but it's just worth noting that those are the correct ways to write them. Remember, we met stress last week, and that was a force over an area. So now, hopefully, visualizing the jug on a box or the brick on a shelf, you can understand how stress and pressure relate. Right? So if you think of the object that was being compressed, and you imagine it as all these tiny slices of object rather than one solid object, the pressure from one slice to the next is going to be that compressive force, that compressive stress rather, and that is the same as how we've just defined pressure. So that's why stress and pressure seem to be the same thing, right? Because they essentially are. Stress is the internal pressure of a solid, whereas pressure generally refers to the interaction between two different substances or objects. So the dimensions, we've already talked about the pressure units. We've talked about the units for pressure, but the dimensions for pressure, just for those of you that have followed along with dimensions, we can use newtons to go back to kilogram meters per second per second. If you ever have trouble remembering newtons, kilogram meters per second, just remember Newton's second law, F equals ma. That's one of those equations that most people don't seem to have much issue remembering because it's very commonly used. That one tells you that Newton's force is equal to mass times acceleration, which is kilograms meters per second. So you can always use that one to get that dimension relation back. And so that means that a Pascal, right, is kilogram meters per second per meter. So one of those meters is going to cancel and we get kilograms per meter per second squared. So the dimensions are mass and then length to the -1 and then time to the -2. So those are the dimensions for pressure. If any unit has those dimensions, it is an acceptable pressure unit. But as I said, SI units are Pascal or newtons per square meter if you want to stick with those. So I'll leave it there. That's the end of the first little video, which, as I said, was just some definitions, some concepts that we want you to grasp. The next video will actually start applying this to different fluids. And then from there, we'll be able to start exploring some of the other aspects of fluid, like fluid flow, Bernoulli's equation, and looking at buoyancy and things like that.